So, very good. Now for the second session of our reunion meeting. The topic of the second session is star-planet interaction and habitability. And we have all our speakers in the panelist room, fantastic. And we'll start right away with the talk by Tyler Gordon. Tyler, please share your screen and tell us all about your research.
Hi, everybody. My name is Tyler Gordon. I'm a graduate student at the University of Washington, where I work with Jim Davenport and Eric Agel. The work that I'm presenting on today is work that I've been doing with Jim on stellar rotation in K2. So let's see if I can, there we go. So I'm going to start off with a brief introduction to stellar rotation and why measuring stellar rotation is important. So this is a plot from McClellan et al. 2014, which I know is a bit busy, but if we just focus on the bluish data points, which show rotation periods for 35,000 Kepler targets, the general picture that we have for rotation is that stars start off spinning relatively rapidly, somewhere on the bottom of this diagram, and then they move upwards as they lose angular momentum via their winds. Until they kind of converge on the bottom of this sequence, and then continue over the course of their lives to lose angular momentum and move upwards. This fact that stars lose angular momentum over their lives means that measuring their rotation periods gives us information about their age. That's what we call gyrochronology. And age is a very important yet often difficult to measure parameter for a variety of reasons. So what we're going to be talking about today and what I'm exploring in the K2 sample primarily is this feature that I've highlighted in the red box. And you can see it a bit more clearly if I remove that red box. It's been called the rotation period by modality. I call it a gap for most of this talk. So this was first observed by McClellan et al. In this 2014 paper. And so what we're doing today is presenting the first robust detection of this feature in the K2 sample. Observing this in K2 is important because unlike Kepler, which just looked in one direction, K2 had many different pointings across the sky along the ecliptic, which allows us to study this feature along multiple lines of sight, which we couldn't do previously. So I'm just going to talk briefly about how we actually measured rotation periods for this sample. If you're interested more in that methodology, then feel free to ask me questions afterwards or contact me offline and we can talk about that. But just to summarize, we started off by calculating the autocorrelation function for each star in the K2 sample and estimating its rotation period from the most prominent peak of the ACF. We then used a Gaussian process rotation model using the rotation kernel, and we ran MCMC on that model. An example based off of how well converged the MCMC was for individual stars and based off of the agreement between the autocorrelation function, period determination, and what we get from the GP model. And so this is what that final sample looks like. This is almost 4,000 high quality rotation period measurements, and each of these has an uncertainty inferred from the MCMC. All right, so now we want to investigate the properties of this gap. So to do that, we actually employ an edge detection procedure, and that's what you can see in the left plot here, where we have rotation period on the vertical axis and Gaia color on the horizontal axis, and we've applied our edge detection to this 2D distribution. And then on the right, we've pulled out the edges of the gap and fit those with a functional form in order to obtain best fit lines for the upper and lower gap edges. Okay, so now, as I mentioned before, the power of doing this in K2 is that we can investigate the location and shape of this gap you know, depending for like pointing by pointing on the sky. So what we do to do that is we ask ourselves essentially, do we have to move these lines, these gap edges up or down or leave them in the same position in order to best fit the trend of the gap in each of the individual K2 campaigns? So this is a selection of those campaigns where I've highlighted in blue the points that are from each campaign individually over a background that shows the full sample for all of K2. So for each of these, we're asking, do we need to shift those lines in order to capture the trend of this gap? And when we do that, this is the information that we get out of that. So I'm going to step back for a minute and explain the details of this plot before I tell you what we see here. So along the horizontal axis, we have the position of the upper gap edge, given in how many days we have to shift the upper gap edge to fit each individual campaign. And then along the vertical axis, we have the same for the lower gap edge, where we're asking how many days in period space do we need to shift that best fit line in order to capture the trend of the gap in that campaign. And then the markers here, each of those represent an individual campaign in K2, and the error bars are estimated from a bootstrapping procedure. And I think what we see here is that for the vast majority of the campaigns, their position in this space is consistent with essentially no offset of either of the gap edges from what we see for the full K2 sample. There are a few outliers, notably campaigns 15 and 18 here. Those are campaigns that capture the Persepi cluster, and so that sequence, that gyrochronology period color space, imprints a signal onto that plot that messes a little bit with our edge detection procedure. So that's why we see those outliers. The others of these are actual outliers, but I will note that if you look at the period color distributions for those campaigns individually, we don't see anything obviously different about where the gap appears in those campaigns. So now I want to talk about a couple hypotheses as to the origin of this gap in terms of our observations for K2. And the first of those that I want to discuss is the idea that this rotation period gap is a result of, that what we're seeing here is actually the star formation history of the nearby Milky Way, or at least in the directions that we're looking. And this is an idea that was forwarded by McQuillan et al. In their 2014 paper, and then was discussed more by Davenport and Covey in their 2018 paper. So to illustrate this, I've boxed out the faster rotating branch of stars below that period gap. The idea would be that these stars formed more recently than the other stars that we're seeing. So these stars would have formed in a burst of star formation sometime in the last 500 million years to a gigayear. And they're evolving just like all the other stars. They're evolving upwards on this plot as they lose angular momentum. And they just haven't yet collided with this population of older stars. So this gap between the younger stars and the older stars would represent a period of time where there was relatively lower star formation. And that would be why we don't see as many stars there. So our K2 observations don't say anything particularly new about this scenario for the existence of the gap, but they do provide an important constraint, and that is that since we see the gap in every direction that we look, any proposal that this is related to star formation would have to explain why that star formation is sort of ubiquitous in the nearby Milky Way. If you're just looking in the Kepler field, for example, you can imagine that perhaps we're looking straight through a burst of star formation. But if we're looking in all directions, then you have to imagine that that star formation happened pretty homogeneously around the sun. Okay, so the other possible origin of this gap that I want to discuss is the idea that this gap is something that originates from spin-down physics. This was also mentioned by McQuillan et al. In their 2013 and 2014 papers. We just heard Ruth talk a little bit about this with regards to the shape of isochrones in that Kepler data. And we also have a sort of physical explanation for this that's due to Spada and Lanzophymy, which they put forward in their 2020 paper. So to illustrate this, I believe you can all see my cursor. I hope you can. just to illustrate this a little bit with my cursor, the idea here would be that stars, as they lose angular momentum, evolve upwards until they hit this faster rotating branch, and then they would slow down or even kind of stall out on this branch before, when they reach the very edge of this gap, they would then accelerate in their angular momentum loss and in a sense kind of skip across this gap or evolve very quickly through the gap before converging on this sequence of slower rotators. So we do see some evidence for something like that happening, and to illustrate that, I'm going to talk a little bit about a couple open clusters. And so I have here in red, this is the Persepi cluster, and these are actually period rotation period measurements from our own code, and I've just highlighted members of the cluster. And in blue, we have the somewhat older NGC 6811 cluster. And what we see here is that stars, more massive stars around a Gaia color of about 1, have continued to spin down between 670 million years and a gigayear, whereas more massive stars appear to have kind of stalled out and not evolved much in their rotation period in that few hundred million years. And the explanation, one possible explanation of that at least, this is modeling done by Spada and Lanzafame, is that we have a mass-dependent core envelope coupling timescale here. So lower mass stars would have their envelopes remain coupled to their cores for longer periods of time. And what that coupling does is allows transport of angular momentum from the core to the envelope that offsets wind-driven angular momentum loss, meaning that those stars would maintain their rotation period as long as the core and envelope are coupled like that. And then the core envelope coupling timescale, since it's mass dependent, would be shorter for more massive stars. So those would become decoupled at earlier times. And when they do become decoupled, they would sort of resume their smooth Skumanich-like spin down. So what you would see over time as these clusters age is you would see this little bit of a ripple propagate upwards and to the right. And wherever that ripple is, that's where you're seeing stars becoming decoupled, their envelopes becoming decoupled from their cores, and you would see them then resume a quicker, come out of that stalling regime and resume a quicker evolution across this gap, accounting for the relative lack of stars in that space. So I think I'm coming to my conclusions here. Yeah. So just to wrap things up, what we've done is detected the rotation period gap in K2, and we've made a very clear detection of that gap that allows us to use an edge detection procedure to measure the edges of that gap with fairly high precision. We've noted that the position and width of this gap appears to be independent of the direction that we look using K2. And now I just want to highlight that that our observations don't have the ability to discriminate between different possible scenarios for the existence of this gap. We actually need additional observations for that. One observation that would be really helpful would be having rotation periods for clusters that are near or even crossing that gap, so that we could actually see how the shape of those gyrochrones changes as those clusters age. And that would be able to inform theoretical understandings of this sort of discontinuous spin down. And that would allow us to calibrate models like the Spada and Lanzafame model that might give us insight into how this spin down happens. And then the other thing that could potentially be helpful here, and this gets to the work that Ruth Angus is doing and discussed just earlier today, which is independent measurements of the ages of these field stars, would be very helpful in discriminating between these scenarios. And that could possibly come from Gaia kinematics. And it sounds like there's a lot of progress being made on that. So thank you.
Yeah, thank you, Tyler. Very interesting work. Would we have a quick 1 or 2 questions for right now? Let's see. If you are among the attendees, please raise your hand. And I see Ruth raising her hand. Ruth, please.
Hello, that was an amazing talk. Thank you so much. I really liked your explanation of the ripple effect. I think that's a really compelling explanation for the origin of the gap. And I wanted to ask, there's also some evidence that the amplitude of variability of stars either side of the gap decreases a little bit relative to the background population. I just wondered if you had any thoughts about that phenomenon.
Yeah, so I think you've asked me this question before, so thanks for asking again. I've actually, after you asked that the first time, I've made some of those plots to investigate that. We don't see anything super clear, but I do see an indication that at least some of the stars in that faster rotating branch do have different amplitudes. They do tend to have slightly, I believe you said, I don't have the plot in front of me, I think you said smaller amplitudes. Yeah, so basically we see a hint that there might be a difference in the amplitude of the variability as you move across that gap, but nothing super clear.
Okay, thank you. And I had forgotten that I'd asked you that before, so you have a better memory than me. Thanks again.
Since we are already going a tiny bit over time, I would ask the people who currently have their hands up and this is, I think, this is only Dan, to type your question into the chat, and we will revisit those in the longer discussion section of the session, okay? Thank you. And also, everybody who has already typed your questions, they are not lost. We will revisit later on.